So good morning one and all. So let us start today's class. So in the last class we have seen Perceptron and its learning algorithm, which means how to learn the weights of the Perceptron. Okay. Now today, so let us discuss something different. So let us see linearly non-separable Boolean functions. So till now we have seen Boolean functions which are linearly separable, which means we can able to draw a line such that it can divide the set of inputs which produce output 1 and a set of inputs which produce output 0. So we can able to draw a line or a plane which can divide the both sets of the inputs perfectly. But so I told you sometimes the given Boolean function may not be a linearly separable. Okay. So example XOR. XOR is a linearly non-separable Boolean function. Okay. We'll see what does that mean. Before that, this is XOR table. Okay. 0 0 means 0, 0 1 0 means 1, 0 1 means 1, 1 1 means 0. It is odd, right? If input contains odd number of ones or zeros, the output is 1, otherwise the output is 0. Now, so you know already, so in Perceptron, single layer Perceptron, so we have a weighted sum. This is x0, which is always 1 with weight w0. It is also called bias. W0 equal to minus theta, that is bias. And inputs are x1, x2 with weights w1 and w2. Correct? So we have a theta, that is bias. W0 equal to minus theta. Anyway, so what is weighted sum? X0 into W0. X0 is 1, simply W0. W0 plus X1 into W1 plus X2 into W2. This is the weighted sum of the inputs. So what do you say? Output, when the output is 1, obviously output Y equal to 1 if the weighted sum is greater than or equal to 0. Here it is 0 if the weighted sum is less than 0. Now, so in XOR gate, when the both inputs are 0 0, output is 0, which means when both inputs are 0, which means this is 0, this is 0. So when both inputs are 0, the weighted sum should be less than 0. Why? Because the output is 0. When output is 0, the weighted sum should be less than 0. In the first row, when inputs are 0, the output is 0. So inputs are 0, so the weighted sum is W0. But it should be less than 0 because output is 0. Okay. In the same way, when the input is 1 1, what is the output? 0. In this case also, weighted sum should be less than 0. Are you getting what I am saying? Okay. So then what do we say? So 1 1. Okay, both are 1, which means the weighted sum is W0 plus W1 plus W2 should be less than 0. So this is equation 1, equation 2, something like you can write down. Okay. So when the input is 1 0 or 0 1, the output is 1, which means the weighted sum should be more than 0 or greater than or equal to 0. So when the input is 1 0, 1 0 means W0 as it is plus W1 should be greater than or equal to 0. W2 is missing because the second x2 is 0. So 0 1 W0 plus W2. W2 because W1 is missing because x1 is 0. That is equal to 0. We have 4 inequalities. What are they? Like this. Okay. So what is the problem here? What is the problem? So from the first inequality, W0 should be less than 0. So from the second inequality, W1 should be more than minus W0. From the third inequality, W2 should be more than minus W0. So from the second and third, what you can say? So from the second and third, W1 plus W2 should be what? If you add second and third, should be greater than or equal to minus W naught. Sorry, minus 2 W naught. Or W naught, whatever it is. But what the fourth condition says? W1 plus W2 should be less than minus W naught. Okay, which means what happening here? The fourth condition contradicts the conditions 2nd and 3. Are you getting what I am saying? So the inequalities are contradicting themselves. So 2nd and 3rd says W1 should be more than minus W naught and W2 should be more than minus W naught. But what 3rd says? What 4th says? What the 4th inequality saying? W1 plus W2 should be less than minus W naught. So these two inequalities are contradicting with the 4th inequality. So that's why we don't have a solution to this set of inequalities. There is no solution for the set of inequalities. Solution is not possible. Okay? Which means you cannot find a solution to the set of inequalities, means this single perceptron cannot classify the Boolean function. What Boolean function? XOR function. What is the problem? Because XOR is a linearly non-separable. It is non-separable linearly. Okay, you can get the same opinion just by looking at the figure. Okay, in the figure, what I have drawn? I have drawn the 4 points. So when the input is 0, 0, output is 0. When the input is 1, 1, output is 0. Okay. Now in the same way, here what do you get? When the input is 1, 0, output is 1. So here output is 1. Here in this scenario, you cannot draw a line such that it can divide the 2 points, 2 set of inputs. Okay. Suppose if you draw a line like this, what's happening? It is not separating blue points and red points. Okay, this line cannot separate blue points and red points. Blue points means which produce output 0 here. Red points means which produce output 1. So the blue or red points are not correctly separated. Why? Because above the line we have 2 red points, 1 blue point. Below the line 1 blue point. So linearly separable means above the line we should have a red or blue points. Below the line we should have a red or blue points. Not combination of both. It is not possible. So can you draw? If I draw like this, it is also not possible to separate them. Okay. Another possibility, if I draw like this, no. This line also cannot separate red points and blue points. Okay, which means you cannot draw a line which can separate these two colors. Okay, you try it yourself. You cannot separate them with a line. Okay, so that's why we say that they are not linearly separable. Okay, the logic is very simple because we have a points at the corners, something like this. Okay, so this is XOR geometry. XOR is a non-separable Boolean function. Okay, so which means XOR cannot be implemented by what? A perceptron, single layer perceptron. Single layer perceptron. What is the reason? Because the reason is not separable, non-separable. Which means a single layer perceptron can only be used to implement a Boolean functions which are linearly separable. Okay. Please remember, I am not saying perceptron, a single layer perceptron. Make a note of this. Because we have only a single perceptron, single layer perceptron. Okay. Now we concluded that a single layer perceptron can only implement linearly separable Boolean function. So if they are not linearly separable, single layer perceptron cannot do anything, right? Now, so we have seen non-separable Boolean function. So let me take few more examples. It is also non-separable. Why? What is the reason? So if I draw a line like this, can this line separate blue and red points? No. So no line or you cannot draw a line which can separate red points and the blue points. Okay, it is also non-separable. So to the above this line we have mostly blue points, but along with blue points we have red points. Okay, now these red points are called outliers. What are called? Outliers. So below the line we have a set of red points mostly, but we have a set of blue points also. So they are called outliers. So whenever there is outliers, so you cannot draw a line such that it can separate them properly. So we can say that they are linearly not separable. But yeah, the thing is, most real world data is not linearly separable. It contains some outliers. Just now I explained the concept of outliers. Okay, mostly in real world data is not linearly separable. It contains some outliers. Okay. In fact, sometimes there may not be any outliers, but still the data may not be linearly separable. Is also very, very important. So it does not mean that if there are no outliers, the data is linearly separable. No. Let us take an example. Here there are no outliers because all the points lie on the red points lie on a circle, all the blue points lie on another circle. There are no outliers, but still you cannot draw a line which can separate both the points. Can you draw a line? Okay, so no line can separate the points, but there are no outliers. They are occupying a particular shape, circle shape. Okay, not possible. So with any of these lines, it is not possible to separate the points, but it doesn't have any outliers because all the points lie on a different circles. They follow a path. Okay, it is also not linearly separable. Even though there may not be any outliers, still the data may be not linearly separable. Okay, don't think that if there are only outliers, the data is not linearly separable. No, it can be any possibility. But so you should know the concept of outliers. These are called outliers. Okay. Yeah. So here we need a model which can deal with the data which is having non-linear separation. Okay. As I told you just now, with a single perceptron cannot deal with such data. We will show that a network of perceptron can deal with such data. Okay, a single perceptron cannot deal with such data. Such data means a data which is not linearly separable, but they can be well designed using a network of perceptrons, which means we take more layers, more number of perceptrons. Okay. Now, so let us go with the network of perceptrons. Okay. We'll take more number of perceptron to deal with the data which is not linearly separable. Okay, right. Now here, so with the two inputs, how many Boolean functions you can design from two inputs? How many? Generally, how many you can design? 16. With the two inputs, you can design 16 Boolean functions. Is it okay? What are they? So here, I have taken x1, x2 are inputs. So here, it is all 0 function. Okay? That is the one Boolean function. Irrespective of input, output is always 0. Here, the last one is all ones. Okay, remaining are AND gate, OR gate, NAND gate, NOR gate, XOR gate, XNOR gate, all those things. Okay, you can find all varieties of Boolean functions here. Total how many? 16 possibilities. Is it okay? You know this thing already. Somewhere you can find OR gate, AND gate, all those things. Okay, NAND, NOR, XOR, XNOR. Okay, these are all possible Boolean functions with the two inputs, which means with n inputs, how many? You can find out 2 power n. In general, with n inputs, you can generate these many Boolean functions. 2 inputs, if n equal to 2, what would happen? N equal to 2 means 2 power 2, that is 2 power 4, that is 16. With 3 inputs, you can generate how many Boolean functions? If n equal to 3, 2 power 3, that is 2 power 8. What is 2 power 8? You can verify. So with 2 inputs, you can generate 16 Boolean functions. In the same way, in generally with n inputs, you can generate 2 power 2n Boolean functions. I think I made a mistake. It is 2 power n. Okay. Now, so among 16, how many are linearly separable? That is the question. Okay. So you can verify how many are linearly separable, how many are not. So obviously we know that just now we have derived which is not separable linearly, XOR, and XNOR also. These two are not linearly separable in case of two inputs. Okay, so except these two, remaining 14 are linearly separable. Okay, XOR and not XOR or XNOR. Okay, so except these two, remaining 14 are linearly separable. What is the reason? The reason is very simple. In XOR and XNOR, so the inputs lie on the edges somewhere here. So they lie like this. Suppose they lie 1 year, something like this. In case of XNOR and XOR, not XOR or not XNOR. Okay, so if you point in this shape, no line can divide them. You try. You draw like this, like this, like this, like this. No. Okay. So except these two, remaining 14 Boolean functions can be linearly separable. So only two are not linearly separable. Suppose, yeah, in this case, how many? Suppose in general, how many are not linearly separable? So for n inputs, we have a 2 power n Boolean functions. Among them, how many are not linearly separable? Okay, you would find out that. But obviously, some of them are not linearly separable. But how many? That is the question. In case of two inputs, two are not separable linearly. In case of any inputs, how many? We don't know the number, but still I can assume that at least some of them are not linearly separable. But how many? That number is required. Okay. Anyway. Right. Now this is the network of Perceptron. Now we will see how to implement a Boolean function using a network of perceptron. Till now we are dealing with only single perceptron. Only one perceptron, right? What was that? Something like this we have drawn. So we have perceptron with inputs, 2 inputs or 3 inputs. So it has got 2 functions. Okay, based on the weighted sum, it takes a decision. Okay. Now, so this is the network of Perceptra. So for the discussion, we assume that true means +1, false means -1. So here what we do is, Boolean means 0 and 1s, no? You know already, 0 and 1. But in the case of 0, we write -1. 1 means +1, like this. Okay, we don't write 0 here. We write -1 +1. We consider 2 inputs and 4 perceptrons. Each input is connected to all 4 perceptrons with a specific weights. Okay. Here we have 2 inputs. These are 2 inputs. Okay. Each input is connected to these 4 perceptrons. Is it okay? Now, now what is the red edge? They are called edges. They are called edges. Red means red edge weight is -1. Blue edge weight is +1. Okay. Now these 2 inputs is each and every input is connected to 4 perceptrons. These 4 perceptron with some weight. What is weight? If it is connected with the red line, it is -1. If it is connected with the blue line, the weight is +1. Here indicated. Is it clear? So 2 inputs are connected to all 4 perceptron with edges with a particular weight, that is +1 or -1. Red line means -1, blue line means +1. Okay. The bias. Yeah. So what is the bias? W0 of each perceptron is -2. Bias is -2. So W0 equal to minus theta, that equal to 2, -2. What is theta equal to? 2. Each perceptron will fire if and only if the weighted sum is greater than or equal to 2. Why? Because theta is 2. The bias is -2, but theta is 2. Please remember this. Which means this perceptron will fire if and only if the weighted sum is more than 2. All these 4 perceptrons will fire if and only if their weighted sum is more than 2 or their bias is -2. So remember, omega naught equal to minus theta equal to -2, but theta equal to 2. What is theta? That is a threshold basically. Whenever the weighted sum is more than the threshold, these neurons will fire, otherwise they don't fire. So what the bias of each and every neuron is? -2. What is the threshold of which each and every neuron is? +2. Okay. Now, yeah, each of these perceptrons is connected to an output perceptron by a weight. Yeah. Now, each of these 4 perceptrons again connected to a green perceptron. It is called output perceptron with some weight. W1, W2, W3, W4. Okay. All these 4 perceptrons are connected to the output perceptron with the weights W1, W2, W3, W4. Okay. Okay. Next. Yeah. The output of this perceptron is the output of this network. Yeah. So the output of this green perceptron Y is the output of this network, entire network. That is the final output. Okay. Now, so let us see what is next. Now, so we need to go with some terminology here. Yeah. So what is the terminology? This network contains 3 layers. Okay. This is a layer 1, layer 2, layer 3, 3 layers. Okay, next. The layer containing inputs is called the input layer. Very simple. What it is called? This layer which contains inputs. How many inputs? 2 inputs. It's called input layer. The middle layer containing 4 perceptrons is called hidden layer. Very, very important. The middle layer containing the 4 perceptrons is called hidden layer. We have one hidden layer here. The middle layer is also called hidden layer. The final layer containing one output neuron is called the output layer. This is a final layer containing one neuron is called output layer. So input layer, hidden layer, output layer. Okay, very simple. Right. Right. Next. The outputs of the 4 perceptrons in the hidden layer are denoted by H1, H2, H3, H4. Yes. We have seen H1 here, H2, H3, H4. What are they? They are the outputs of the 4 neurons in the hidden layer. They are the outputs of these 4 neurons or perceptrons in the hidden layer. How many are there? 4 perceptrons and 4 outputs. What are they? H1, H2, H3, H4. But what are W1, W2, W3, W4? They are weights of those 4 perceptrons. These are weights. These are outputs. Okay. The red and blue edges are called layer 1 weights. Yeah. These are edges, no? Red and blue. They are called layer 1 weights. What are the weights? Red means -1, blue means +1. They are the layer 1 weights. What are these two? W1, W2, W3, this is called layer 2 weights. I already told you. These are layer 2 weights. Okay. Next. Yeah. So we claim that this network can be used to implement any Boolean function. Now, so in the starting itself, I told you, using a single perceptron, you cannot implement this XOR, XNOR because they are not linearly separable. But what we want to say is, using this network of perceptrons, using this network, we can implement any Boolean function irrespective of whether it is linearly separable or not. That is what I want to prove. Okay, I don't mind whether it is linearly separable or not, but I can surely implement any Boolean function using a network of perceptrons. Okay. Yeah. So each perceptron in the middle layer fires only for a specific input. This is very, very important. In this middle layer, we have 4 perceptron. It will fire for a specific input, not for all inputs. Okay. Now, this first perceptron will fire for -1, -1. For 2 red lines, it will fire. Why? Because what is the reason? If input is -1 and -1, and it is connected to the first neuron with 2 red lines, weights also -1. What is the weighted sum? 1 plus 1. -1 into -1 plus -1 into -1. This is 2. Now obviously the weighted sum should be more than or equal to 2, no? It will fire. In the same way, the second perceptron will fire for input -1 plus 1. The third one for 1 plus 1 minus 1. The last one is for +1 plus 1. Okay. So each and every neuron or perceptron in the middle layer will fire for a specific input. Okay. So no 2 perceptrons will fire for the same input. Please mind this. Okay. No 2 perceptrons will fire for the same input. each perceptron in the middle layer or in the hidden layer will only be fired for a specific input. What is that input? What is that input? First, perceptron will fire for -1 -1. It is for -1 +1. It is +1 -1. It is for +1 +1. Okay. What is the reason? So obviously, for these inputs only, the weighted sum is greater than or equal to 2, or at least equal to 2. Okay. Now let us see, can this network of perceptron will implement XOR or not? The question is, can this network of perceptron will be able to implement XOR Boolean function or not? In the starting itself, I told you that a single perceptron cannot implement. What is the reason? We have a set of inequalities which are contradicting with themselves. I told you, so we have inequalities which are contradicting here. It is the case of a single perceptron. Now we have a network of perceptron. Now let us see whether this can implement XOR gate or not. Okay. Yeah. So this is XOR output. Okay. 0 0 means -1 -1, something like that. Okay. So 0 0 means you know already. If it is 0 0, output is 0. Yeah. Let us go back to this. Yeah. So -1 -1 means 0 0. Okay. So when the input is -1 and -1, this will fire. So when the input is -1 +1, it will fire. +1 -1, it will fire. +1 +1, it will fire. Okay. Firing means H1 equal to 1. Here firing means H2 equal to 1. Firing means here H3 equal to 1. Here H4 equal to 1. Okay. So -1 -1 means when input is 0 0, H1 is 1. Okay. Input is 0 1 means H2 is 1. Input is 0 1 means H2 is 1. 1 0 means H3 is 1. 1 1 means H4 is 1. Okay. So very clearly indicated that each and every perceptron in the middle layer will fire only for specific input. H1 is 1 only for 0 0. H2 is 1 only for 0 1. H3 for 1 0. H4 for 1 1. Okay. So here assume that 0 means -1. I told you in the starting itself. Okay. But what is the XOR output? Very clear. Okay. 0 0 means 0. 0 1 means 1. 1 0 means 1. 1 1 means 0. Okay. So here XOR output means output, the final output. Okay. What is H1? Output of the middle layer perceptrons. Right. Right. Now. So here. Now. So what will happen here? Yeah. So to this perceptron, what is the weighted sum? Okay. So this is output layer perceptron. What is the weighted sum? W1 into H1. Okay, because to this perceptron, what is the input perceptron? These 4, not this. Please remember, it's second layer, no? We are third layer. For this layer is input. Okay. Now, so for the output perceptron, the weights are W1 H1. The weighted sum is W1 H1 plus W2 H2 plus W3 H3 plus W4 H4. Okay. Obviously, so by default, so we take W0 H0. Okay. H0 happened to be 1. So simply W0. Right. Now the weighted sum. So in the first row, what is the weighted sum? What is the weighted sum? So W1H1 plus W2H2 plus W3H3 plus W4H4. What is that? W1 only, because remaining H are 0. In the second row, W2 is left, remaining will be 0 because all are 0. Third row, W3 will be left. Fourth row, W4 will be left. Okay, are you getting or not? So let me write. If you have any problem, let me write here. The first row only we are left with W1. This is the summation I equal to 1 to 4 Wi Hi. Okay, W1 first row, second row W2, third row W3, fourth row W4. What is the reason? Here we have only H1 that equal to 1 in this row. Remaining are 0. H2, H3, H4 are 0. In the second row H2 is 1, remaining are 0. So and so. Okay. So this weighted sum is simply very, very important. Okay. Now, so we got a weighted sum for this output perceptron, which is in the output layer. Okay, let W0 be the bias output of the neuron. Okay, that is the bias. Okay, obviously, so the output neuron will fire when the weighted sum is summation I equal to 1 to 4 Wi Hi is greater than or equal to W0. If it is so, the output will be 1. The output neuron will fire. Otherwise, it won't. This is the logic. Okay. Please remember. Now, this results in the following 4 conditions to implement XR. Okay. This results in the following 4 conditions. Okay. Now, before that, now what should be the final output? See, we are implementing XR Boolean function using the network of Perceptron. Finally, output should be like this. This column. Third column. What are they? 0, 1, 1, 0. Okay. Here output should be 0. Here 1, 1, 0. Is it okay? For output to be 0, this should be what? For output should be 0, the weighted sum should be less than W0. Are you with me or not? Okay, which means, but what a weighted sum? In the first row, W1, that should be less than W0. So second row output should be 1, means the weighted sum should be more than W0. But what a weighted sum? W2, that should be more than or equal to W0. It is also W0, it is less than W0. Now we have a set of inequalities. Still we have set of inequalities, but how are they? What are they? So W1 is less than W0. W1 is less than W0. W2 should be more than or equal to W0. W3 also should be more than or equal to W0. W4 also should be less than W0. But the logic is they are not contradicting. We can able to find the weights so that they can satisfy these inequalities. Unlike before, there are no contradictions now and the system of inequalities can be satisfied. We don't have any contradictions, but we had contradictions when you use a single perceptron. Here. But here we don't have any contradictions. Okay. Essentially, each WI is now responsible for one of the 4 possible inputs and can be adjusted to get the desired output for that input. Okay. So we can adjust them, all the weights, so that these inequalities will be satisfied. Okay. Choose properly the weights. W1 is less than W0. W2 is more than or equal to W0. W3 also more than or equal to W0. W4 is less than W0. Choose these weights or adjust these weights properly so that these inequalities are satisfied. There is no contradiction. So we can get a solution for these inequalities. Okay. So solution means we can implement XOR Boolean function using a network of perceptrons. Which means using a network of perceptron we can implement any Boolean functions which are not linearly separable. That is simple logic. But using a single perceptron, you cannot implement a Boolean function which is not linearly separable. But we can do same thing by using a network of perceptrons. Okay. Now, so it should be clear that same network can be used to implement remaining 15 Boolean functions also. Very important point. Using this network of perceptron, we can implement all 16 Boolean functions, irrespective of whether they are linearly separable or not. Okay, what are those 16 Boolean functions? All these Boolean functions can be implemented by using a network of perceptron, irrespective of whether they are linearly separable or not. Okay, all two inputs of Boolean function can be implemented using a network of perceptrons. Right, that is proved. Now, so what happens if we have more than two inputs? Okay, suppose we have three inputs. Three inputs. How many Boolean functions? I told you 2 power 8. So among 2 power 8 Boolean functions, some may be linearly separable, some may not be linearly separable, but all 2 power 8 Boolean functions can be implemented by using this network of perceptron. But here we have input layer, one hidden layer, one output layer. Input layer contains 3 inputs and the hidden layer contains how many? 8 perceptrons. Output layer contains 1 perceptron. Why 8? 2 power 3. So in the hidden layer or middle layer we have a 2 power n perceptrons. Why? Because in case of 2 inputs we have how many perceptrons in the middle layer? 4. Why 4? 2 power 2, which means 2 power n. Okay. So in the output layer we have only 1 perceptron. And what is the bias? -3. Okay. When this will fire? When input is 0, 0, 0. 3 inputs, no, 3 bits, no. 0, 0 means -1, -1, -1. When the last neuron will fire? When this will fire? When all are positive, 1, 1, 1. So same thing, just extension. Okay, all red lines means -1, all blue means +1. These are 8 weights. Okay, but here, so this is the for the 3 inputs. With this you can implement 2 power 8 Boolean functions irrespective of whether they are separable or not linearly. Okay. Now, so this is a theorem, very important. Please read it properly. Any Boolean function of n inputs can be represented exactly by a network of perceptrons containing one hidden layer with 2 power n perceptrons and one output layer containing one perceptron. What I want to say is, any Boolean function of n inputs can exactly be represented by a network of perceptrons containing one hidden layer with 2 power n perceptrons and one output layer with one perceptron. So what I want to say is, any Boolean function with n inputs, n equal to 3, can exactly be represented by a network of perceptron containing one hidden layer, only one hidden layer, containing 2 power n perceptrons. Here 2 power 3, which means 8 perceptrons. We have 8 perceptrons. Along with that, one output layer containing one perceptron. Total, how many perceptrons we have? So in the middle layer and hidden layer, 2 power n, plus in the output layer 1. Total perceptrons are 2 power n plus 1. It is for 3 inputs. 3 inputs means 8 plus 1 9. 9 perceptrons. Okay. For 3 inputs 9 perceptrons. For 2 inputs, how many perceptrons? 4 plus 1 5. Obviously 2 power n plus 1. If n equal to 2, 2 power 2 plus 1 5. Okay. That is the logic. A network of 2 power n plus 1 perceptrons is not necessarily but sufficient. Okay, very important. So, a 2 power n plus 1 perceptrons are not necessary. It is only a sufficient condition. What do you mean by this? Even though you do not have a 2 power n plus 1 perceptron, still sometimes you can implement a Boolean function of n inputs. Example is AND gate. AND gate, OR gate. AND gate or OR gate. So we implemented them using, if you go back, you check 2 inputs, x1, x2. We implemented this OR gate using how many perceptrons? Only 1. Go to the previous class and check. We implemented OR gate using only 1 perceptron. How many inputs are there? 2 inputs. Okay, which means, so this is not a necessity. It is sufficient condition. Okay, it is not a must. That is the logic. Okay, as n increases, the number of perceptrons in the hidden layer obviously increases exponentially. Okay, so in the hidden layer we have a 2 power n perceptron. Obviously n increases, the number of perceptrons in the hidden layer increases exponentially. Okay, you should take care of that. Yeah, so this is called multi-layer network of perceptrons, simply MLP. So the network of perceptron, all this thing is the network of perceptrons. So it is called a network of perceptrons, are also called multi-layered perceptrons, MLP. Multiple layers are there, that's why it's called multi-layer perceptron. In the shortest form, it's called MLP. Yeah, specifically, it tells us that an MLP with a single hidden layer can represent any Boolean function. Yes. An MLP with single hidden layer. We have only single hidden layer. Please remember. How many hidden layers are there? Only 1. We have 3 layers. That is okay. How many layers? 3 layers. Input layer, hidden layer, output layer. But we have only 1 hidden layer. So an MLP with 1 hidden layer can implement any Boolean functions irrespective of whether they are linearly separable or not. That is a simple logic. This is called the representation power of a network of perceptron. Okay. It indicates the representation power of a MLP with a single hidden layer. Please remember, it is MLP with single hidden layer. Let me write here. One hidden layer. But in hidden layer, we have a 2 power n perceptrons. Okay, that is the logic. Okay, so with this we stop here. Thank you.